I don't share a screen until
after. Yep.
let me do it. Okay.
Hey, good morning, Barry. How are you?
I'm well, thanks. Rich, how are you?
I'm doing great. So we got a bunch of people already in the room. Many names I'm familiar with. Hey, Giuseppe. Good to see you in the room. Many have already been to a bunch of our events, so I'm expecting more and more will continue to kind of come in as things continue. So I'd like to just introduce the event and welcome to excuse me, selecting the correct carbon composite AFO, powered by LER Expo. My name is Rich Dubin. I'm the founder and publisher of Lower Extremity Review Magazine and the CEO of LER Expo. I've personally been in the lower extremity space for over 30 years. I'm just so honored to be working with custom composite manufacturing to facilitate this awesome educational event. But before we get started, I always love to know and ask where everybody's from. So if you wouldn't mind keying in the little chat there, let us know where you're from. Hey, Giuseppe, that would be great. Good morning, Huntington Beach. I love Huntington Beach. Beautiful surf out there. I don't surf, but I like to watch the surfers. Yeah, where are you all from? Just key it in the lower right. Let us know. Love to hear. Ocala, yep, Florida. Fort Myers, got a couple Floridians down there. Hey, Becky in Houston. Jeff, near Tampa, nice. It's actually, it's probably hotter here right now than it is down there. Barry, hey, Barry, how are you? No, Barry's been to a bunch of events. Ohio, Norway. Oh, Lewis, all the way from Norway. That's awesome. CPO from Norway. Love it. One of the cool things about doing the events like this is that you get people from all over. Hey, Ted, welcome from Des Moines, Iowa. Bangkok. Wow, what time is it in Bangkok right now? It's got to be tomorrow, like maybe mid-afternoon tomorrow, right? They're like 28 hours ahead. Yeah. Good. Well, welcome. Glad you're here. So I'll just go over a few little, points on the platform so you just know how to navigate between the different components. Obviously, the chat is in the lower right. You can see that. You get to that by clicking on the comments in the upper right. If you click on people, you can see everybody that's in the room. You could say hello to any of your colleagues, people you haven't seen in a while, like that. There's a little chat button or a little chat box in the upper right next to your profile. That'll tell you if you get a message, so you can message your colleagues or anyone that's in the room. Feel free to do that. You have any questions? We're going to take questions during the roundtable. So after Barry speaks and then after Ross speaks, we're going to have a little bit of a half-hour Q&A at the end, which I think will be great. So try to save your questions for that. And then the three emojis. These are important because they give the speaker and us a sense of how they're doing. So if Barry says something funny, you can click on that. If he says something enlightening, which I hope he does, and I'm sure he will, and get enlightened, and then if you want to clap, you can clap. One of the cool things I also love about our platform, and I hope everybody takes advantage of it, is grabbing the mic. So if you do have a question, we'd love to see you. Part of one of the things that, we want to be as close to we can as being in person. And so if you grab the mic, come up to the stage, ask your question in person, that would be awesome. We'd love to see you. So I want to introduce Barry McCoy. Barry is a CPO and the president of Custom Composite Manufacturing. He's got a great presentation, and I'm going to turn it over to you, Barry.
Thank you, Rich. If I can do this correctly.
Yeah. If not, I'll help you. Perfect.
Let's see.
Pro. There you go. Awesome. Take it away. I'll see you guys after. Enjoy the presentation, and glad you're all here.
Well, first of all, thank you all for joining. This is a new adventure for me, and Rich is an old pro at this, but this is a new adventure for me. And this has to do with the selecting the right carbon fiber AFO. Most of you are familiar with plastic or olefin-based AFOs. These are oil-based plastics that we've used for years, probably 50, 60 years in our industry. You can see that some of these are you're familiar with. This is a jointed AFO here, and it has a posterior adjustable posterior stop in the back. These are very common. This is more of a solid ankle design here, and this is a PLS design, mainly for drop foot, and we'll talk about that as well. But these AFOs in terms of the fact that they're monolithic structures. In other words, you select basically the thickness of the plastic, whether it's 1/8 inch or a 532, a 1/4 inch, whether it's polypro or copoly or some other plastic that you're familiar with, and you would heat that up in an oven, and then you drape it over a positive mold. But the strength of the structure really has to do with how thick the plastic is. And so you're basically stuck with the thickness of the plastic throughout the whole structure. A composite brace is much different. On the right side of the screen here, as you're looking at it, so this is the composite brace that we're building right here in the background. And there are certain things that we put in the strut, certain types of materials we put in the strut. There are other types of materials that we put in the foot plate. This is the section of the calf band. This is also goes into the foot plate. And there's a couple other things that we've kind of left out, but have to do with the structural integrity of the brace, of the AFO that we're making. The point is that these are all components. And we can have a stiff component in this section, and we can have a very flexible component in this section. We can also have a flexible component in the calf section as well. It depends on what your patient needs. If you have a patient that has, let's say, recurvatum at heel strike, we can make the calf section very stiff, so it pushes the calf forward, the knee forward, and helps prevent increased recurvatum during their initial part of first rocker. But so there's a lot of variations that we can incorporate into an AFO that you can't do in a monolithic structure. You're basically stuck with one strength component throughout. So here is a patient that is wearing some AFOs, and she's wearing an articulated AFO with a plantar flexion stop in the back. She has Ehlers-Danlos syndrome, which leads to very lax joints, and apparently she's had some ankle strains and sprains, and so rather than continue to endure those, she just has AFOs to kind of keep her ankles from deviating too much during gait. But one of the costs of plastic AFOs, or the hidden costs, we don't think about them too much. One of the costs of plastic AFOs is trying to get shoes to fit over them. And here's her little testimony about that. It's kind of humorous.
Their pairs. They usually take about 6 months until there's about a rip or a hole to get demoted to everyday use, not going to work in. And then if they really get disgusting, they get demoted again to camping. Shoe companies like step up, man. Going into a store and sitting there for 2 hours, like, it's terrible. And finding a brand, a line of shoes, this isn't something where it's like, oh, just you can wear flip-flops or something. Like, you have to wear shoes with these. Why can't I find shoes that fit? So I'm probably set for a little bit here, having 4 extra pairs. But really, like, hey, yo, Airwalks, you guys got any extra rider's shoes? I'll buy them. Some people with AFOs can just wear whatever shoes they want, and then other people with AFOs are so limited to their shoes, and then it depends on their money. I'm sure New Balance and some of those other brands, I'm sure I could go out and buy them and they would work. I just have to think about price. At least the Airwalks, I mean, they were never really that expensive. I think the most I spent was like maybe $35, and then with them on sale, it could be like $15. Anyways, if you get anything out of this video, shoe shopping can be very frustrating, but it's quite necessary for people with AFOs. And also, Airwalk. you have anything extra, I'll take them. I would love to have days where I'm not wearing the same shoe every day for 6 months. I'm just saying, it's just an idea.
So that's her idea. And she's not really asking for a whole lot. She's asking to wear a skateboard shoe, essentially. And so that's a pretty pretty loose definition of a functional shoe for a young lady. I just think it's kind of interesting how she demotes her shoes from everyday use to a little bit of use and then to camping. I didn't know camping was a problem. I guess you wear junk shoes to go camping. So, so is there an alternative to plastic is the question. And for the last 15 years, we believe that there is. I've been interested in advanced composites for 20, 25 years. And in our state, I'm in Rhode Island, and back then they were building America's Cup boats right in our backyard, just a half hour away from us. And one of my patients actually, her dad worked for an America's Cup boat builder down in Bristol, Rhode Island, and I got to be very friendly with him. And he was the one who actually started me off in applying carbon fiber to AFOs. So why should we look for an alternative? Well, the materials that are used are just incredible. They're very high strength to weight ratio, and the energy storing and return properties are just amazing. And I just want to kind of give you some idea of what I mean by that. This is America's Cup boat racing. This happened this January in Australia. The New Zealand's won the America's Cup last time. So the rules in America's Cup boat racing is that if you win, you get to pick the design for the next round. And so the design that they picked was this foiling monohull design. There's just one hull, and there's these arms that project into the water, and you can see how quickly these boats turn. They can turn on a dime, and they're going 35 to 40 miles an hour at certain points throughout the race. There's a lot of tactical issues as well, but the amount of forces on these arms are just tremendous. This boat it weighs 7.5 tons without anybody in it. That's 15,000 pounds. And what that means is that this arm right here has to bear all of that weight. So you've got 15,000 pounds just to get the boat out of the water. And you also have the weight of this, this is part of the boat weight, but you also have the force of the wind that is coming in this direction here. And so this is like an airplane wing that's mounted vertically on top of this hull. And there's a tremendous amount of force that is being taken this way. And all of it is being borne on this foiling arm that goes out into the water. And this is the only thing that is supporting the boat up, keeping it out of the water. There is a rudder in the back, which has to do with, there is a little bit of a foil on the back of that too, which supports the back of the boat. But this is the main structure that supports all of this weight and all of this force. They've done destruction testing on these, and they have them so that they can endure 26,000 pounds before they get destroyed. So there's quite a bit of pressure that's exerted on this arm. So that's the first part of the carbon fiber component, is that this tremendous strength to weight ratio that you have. The other component has to do with energy storage and return. Same type of material, same carbon fiber, only there is a tremendous amount of energy that can be stored in that pole vaulting pole, and then it is released. So as this athlete runs down the I guess it just happened once. I thought it was going to repeat. But there's the pole bends in an arc, and then it releases and pole vaults them over the pole itself. So there's a tremendous amount of energy that can be stored in carbon fiber and then released. So these two components together are really what's important to make I think they can make a really great brace for somebody. And I think that we're not trying to duplicate what we've done before in plastic. So we have about 12 different designs we've come up with over the years, over the last 20 years of making these, and they all have a specific function. And that's why I think it's important that we understand the difference between, plastic bracing and carbon fiber bracing. We've had design goals that we started to that we've had for years, and we want to make the lightest brace possible for the existing pathology. Most of our braces only weigh between 6 and 8 ounces. Once in a while, you get a very tall person or a very heavy person, and we have to use more carbon fiber, and so that might be pushed to maybe 9 ounces or 10 ounces. But that's fairly uncommon. Most of the average patients get away with about 6 or 7 ounces of actual weight in the brace. We want it to be stiff enough to provide support for the pathology that the patient comes in with, and we want it flexible enough so it doesn't interrupt rockers of gait. And that's important, especially if you look at any solid ankle AFO is going to kind of interrupt the first rocker of gait. It's going to just cause a knee flexion moment, and I'm sure there are instances where you can put a joint in there and kind of reduce some of that. But most of the plastic braces that don't have a joint interrupt the rockers of gait in some way. We want it to be low profile as possible, and this is what we talked about, or what the girl talked about. We want it to fit easily into shoes. I think you could make a solid case to say that if a patient is balking at paying a copay for a carbon fiber brace, they would probably pay the same amount in copay in trying to find shoes that fit for plastic bracing. So I think you can make the case that you can use your present shoes without too much issue when it comes to having them use a carbon fiber brace. We want to give the patient the most natural gait they can, and I think as you listen to Ross and to some of the case studies that we've been through, you'll see how natural the gait looks when you do it. It's not just the material that's important, though. It's the process that is used to make the material. We use pre-preg carbon fiber exclusively. We don't use any liquid resins. The resin is already in the material when we buy it. We buy it from a number of national companies that make carbon fiber, and it comes to us frozen. So we take everything and put it in a freezer, and the reason that's in a freezer is because we don't want the resin to activate. If you just left it out on the shop floor for 30 days, it would become hard as a rock. So in order to use pre-preg, the processes, these two processes here, you have to have freezers that hold all this stuff when you order it. The lamination stuff is something that you're probably familiar with in prosthetics. You're going to put a little bit of resin inside a PVA bag, and then you would string it down over the socket area, and then you'd wait for that to set, and then that would be your plastic. Or you can use carbon fiber. This has got some nylon on it too. You can use carbon fiber that way, but the characteristics of a wet layup are much, much different than a pre-pregged autoclaved method. This is not a pizza oven. It's like a submarine, but this is the autoclave that we have in our shop. There's a heating element in the bottom. There are temperature sensors or temperature probes here, and there are vacuum lines and vacuum probes on this side. All of this is important because it's a controlled process. Everything is part driven. We want to know, or we do know, the exact temperature of each part that is in there at any time during the cook cycle, and that's something that is just inherent within the process of making with an autoclave. This is a hot air oven. You can do a pre-preg oven. You can cure things in a hot air oven inside of a nylon bag. And we used to do this probably 15 years ago. before we were invested in this autoclave. But this is the key to making very responsive, dynamically responsive AFOs. There are fabrics that we use, and there are several of them. This is fiberglass or e-glass. This is the one you're probably most familiar with here. This is the 2x2 twill. The fibers run. The fibers run at 90 degrees to each other, and there also are unidirectional tapes like here. This all the fibers run in one direction. So if you really want strength in one specific direction, you would use this uni fabric in certain areas of the AFO. When you buy these things, it has all of these different numbers here, and this is the one that's probably the most important one right here, and that is it only has 35% resin content. That's what it starts with. And during the process, we're able to suck out another 2 or 3%. So we're down to close to 30% resin content. And that's the reason you want low resin content, is because it gives you a much different dynamic response when you have very low resin content. If you have very high resin content, you get something that is stiff, but it's brittle, and it doesn't bend and move the way you want it to move. This is a cutting table that we have in our shop, and most of the AFOs that we make involve about 20 or 30 different individual pieces. And I say 20 to 30 because a lot of it has to do with the height, weight, and activity level of your patient. Obviously, the higher weight they are, the higher their activity level, the more carbon we're gonna need in order to make an efficient AFO. But unless you want to get carpal tunnel syndrome in a heartbeat, you need to have one of these tables that will cut out preformed patterns that we use in making the AFOs that we make. The real advantage of an autoclave is that it not only cooks the AFO at a certain temperature, which it has to in order to arrive at a final product, but it also increases the pressure. It's a pressure vessel. That's the reason it's a round cylinder. It looks somewhat like a submarine, but we're able to pressurize that, and what all that does is compact the carbon so it's extremely dense. Most wet layups you use vacuum. If you got maybe 15 psi in a vacuum chamber using a wet layup AFO, that would be average, I would say. But we're cooking AFOs at 100 psi, so it's about 6 times the compaction that you get with an autoclave. This is all computer controlled. These are recipes that we have that are in our computer that controls the autoclave, and each one of these is important because there has to be a ramping of the temperature at a certain rate. If you ramp too fast, there are problems with the AFO. If you soak too long, there is a problem, or you don't soak long enough, there'll be a problem with the AFO. And then there has to be a curing part right here. This all has to do with minutes at the bottom, and everything is part driven. These are all data that's given by the temperature gauges, the vacuum gauges, and the pressure gauges that are inside the autoclave. So it's not like we went down the street, bought a pizza oven, and started playing with carbon fiber. This is a controlled process. This same controlled process is used by Boeing. It's used by Airbus. It's used by many sports industries. So this is a well-documented and well-defined process that is used to make AFOs. Here's the reason why autoclave method is better than any other method. It has precise control over the material. It's an engineered material. It's an engineered resin. There's a certain percentage of content of resin per square meter of fabric, and so all of that is important and integrated into the function of the AFO. We have greater compaction, lower percentage of resin. That results in a device that is low profile. It's lighter than anything else you can do in plastic. It's stronger, and it's more dynamically responsive. So when you think carbon fiber, think of that last line that you have there. It's what you're really looking to accomplish, or what you will accomplish if you use a prepreg carbon fiber AFO. I was trying to figure out a way to how to dynamically show you the difference between dynamic response and stiffness, and so this is a little video that we made these a couple days ago, but they're two identically shaped foot plates. That's how much flexibility you can get, and that's about a 10-inch foot plate, as you can see it there. All we did was add about 3 layers of uni tape in there, and I can barely, you can see my fingers turning white as I'm trying to bend that thing, but we can adjust and vary the amount of flexibility and stiffness in each segment of the AFO in order to meet your patient's needs. There are some things about foot drop that have irritated me for years, and and I want to show you some things that I think are important, especially for foot drop. If you just have a basic foot drop, someone has had back surgery and they can't pick up their foot for some reason, or if they've had a peroneal nerve palsy or something like that, and they just need something to pick their foot up. We don't believe in enclosing the heel. And what I mean by that, when you use plastic, you've been closing the heel for years. You've used that little heel cup in order to provide a lot of structural and geometric shape to that section of the AFO. It may be very thin in the Achilles area, but every time a patient takes a step, this is high speed running on a treadmill, you can see that there's a lot of valgus that goes into running just as from between first rocker and second rocker. Now there isn't much of a first rocker here because he's running, so he almost goes to foot flat. But you can see when he's unilateral weight bearing, there's a lot of valgus that goes in. Not a lot, but there's a small amount of valgus that happens during second rocker, between first and second rocker. The reason why that is important is that when you enclose the heel, and what you're doing is that your patient is just getting irritated every time they take a step, and their heel is kind of rotating inside that heel cup. And if as the temperatures get warmer, you've got a lot of friction and a lot of heat that goes into just walking down the road when you have the traditional classic PLS design plastic AFO. In order to make things more comfortable for the patient, don't enclose the heel in any way if there's just a foot drop problem that the patient has. Now, I have to admit that there are some times when you want to control the amount of valgus that a patient has. And we have several ways of doing that, and we'll get into that as we get more into the day. But just for someone who just has foot drop and you want to give them a brace that functions well and alleviates their problem, then you can do all of that with a carbon fiber AFO that doesn't enclose the heel. The reason, again, is because the weight line in unilateral weight bearing runs medial to the hip, medial to the knee, and lateral to the ankle joint right here. It's lateral to the ankle joint. And what that means is that this weight line is going to produce that pronation or that valgus motion at second rocker when there's full weight bearing. So just for foot drop again, 3 muscles primarily responsible for foot drop: tibialis anterior, flexor digitorum hallis, and flexor digitorum longus. These are the 3 that are primarily responsible for foot drop. But you can accomplish this arc that's going on here, a lot of motion in this area, and very little motion by the strut. And you can accomplish all of that and simulate normal normal ankle motion without a joint because you have a progressively flexible foot plate. In other words, it's very stiff in this area and it's very flexible in this part of the foot plate. So that simulates or what it does is that it mimics the eccentric contraction of the dorsiflexive muscles between first and second rocker. So the dorsiflexive muscles have two functions. One is to pick the foot up during swing so it doesn't hit the floor. The next one is that heel between first and second rocker. There's an elongation of those muscles in a controlled fashion, controlled plantar flexion, as the foot comes down to the floor. So here's a foot drop patient, and you can see he doesn't really have a first rocker. He just goes straight to second rocker, and he has a little bit more knee flexion on the left than he does on the right because he's trying to clear the floor. And he has very asymmetrical gait. Is that the right side gait is longer than the left side, and he's doing a pretty good job disguising it all, actually. You put the brace on, of course, there's the immediate reestablishment of first rocker. He has heel strike. There's controlled plantar flexion between first and second rocker. And his gait is symmetrical again. And he doesn't have that hiking of his knee. He doesn't flex his knee in order to clear the floor. So if his pant leg was down and you didn't see that 7-ounce AFO there, you would think he's a pretty normal walking person there. And here's a good demonstration of reestablishing first rocker. Again, he's using the same shoes that he came into your office with, and he's fitted with the brace. There isn't much of a structural component that goes down into the shoe. There's a strut on the lateral side, and that thinning of the foot plate, a progressively flexible foot plate. Restoring plantar flexion is also something that is really something you can do with carbon fiber. This is high-speed running again. Then you'll notice that right at the end of second rocker to third rocker here, there's a little bit of a plantar flexion that happens right there. And there's been some braces that have been made in recent years that have addressed this. The one is the IDEO brace made by Ryan LeBlanc. It was done in the Center of the Intrepid down in Austin, I think, Texas. May not be sure of the location there. But he also, I think, now works for Hanger Clinic. And they've come up with this posterior spring thing that is in the back. And it's made for running. And we've made a similar design, but it has a different heel section. And we'll get to that in a second. And this is our design here. It has an inverted Y just above the heel, right here. And that's purposeful because we want the heel to be soft at heel strike. We don't want to initiate a lot of knee flexion and heel strike. And as you can see here during running, that this thing really bows backwards this way. And that's what provides that. It's that pole vault idea, only on a much smaller scale, is that as the carbon fiber bows back and stores energy, and then at the end of second rocker going to third rocker, it releases that energy in order to help propel them down the road. But this design not only helps restore plantar flexion, but it also doesn't really interrupt the rockers of gait. Back to those design goals that we mentioned earlier. We're not making specific braces just for running. It's not that we couldn't. We could certainly do that. If you have a patient that really just wants to do running, we would probably plantar flex the foot a little bit, load the strut up a little bit earlier in the gait cycle, and so that when at the end of second rocker, he would have quite a bit of energy stored in the posterior spring. So all of that is possible. But for normal folks that have a plantar flexion weakness and just want it restored for normal walking, this design works incredibly well. This is a CP patient who wanted to play basketball with his friends. So we made this posterior strut designed for him. It seems as though he's got an awful lot of stuff in his pants, like a wallet and a cell phone and maybe a couple of spare baseballs. But every time he runs, his pants fall down a little bit, and it's a little bit irritating. But again, you can see here that the strut goes away from him in order to help propel him forward. The distinguishing difference here is that because he has CP, he had a little bit of a crouch gait. So these braces were made in about 10 degrees of dorsiflexion, maybe even 12 degrees of dorsiflexion. But that was helpful to him because it helped him run pretty fast, and he was able to play basketball and keep up with his friends. He loved basketball. I just wanted to have some alternative to plastic bracing that would help him as he played basketball with his buddies. But again, it's that customization of those principles that we've talked about earlier that make it valuable for your patients, so that they can do what they want to do in life as far as that is concerned. So I'm sure a lot of you say, well, there isn't a whole lot of ankle control going on in these braces, although we can build ankle control into the braces. The first way of controlling the ankle, we usually put, in other words, if there's a varus, and Ross Workman will get into this more when we see some of his case studies that he's been doing. But the first thing is just having a lateral wedge on an insert. Sometimes that's all you need to pitch the whole ankle complex toward the strut, and it kind of stabilizes it. If you need more than that, you can use the wedging idea and the supramalleolus strap here to control the malleolus and hold the ankle toward the strut to stabilize the ankle complex that way. If you need more than that, we have made these. These are ProFlex SMOs. They're actually half of an SMO. And they would actually link the footbed to the ankle strap. So you have this physical connection here. And you can use that to really control either valgus or varus of the ankle when it comes to controlling if you really need a lot of control over certain portions of the anatomy. We have tried different materials here. We've tried polyethylene, we've tried polypropylene, but these materials are just way too stiff. And in fact, the polyethylene and polypropylene will crack at the metatarsal heads because there's so much motion in the carbon fiber foot plate. Over time, it just cracks. So we need somewhat of a flexible material to use to make ankle control when we use carbon fiber. But that has worked extremely well if you need that amount of ankle control. Again, we try to stay away from that because one of our goals is to make it fit easily into the shoe. And when you have all this stuff that goes into the shoe, it makes it difficult for patients to use their regular shoes when it comes to that. Partial foot designs, we have a couple of them. One is the TMA design that we have here, and these are for TMAs and maybe some long Chopard patients or Lisfranc patients. Sorry, this posterior opening design here. This is more for the Chopard Lisfranc design. This assumes that there isn't really any usable ankle motion. This brace here, this idea here assumes that there is usable ankle motion because we want to preserve that. Some of the things that we really need to consider is all partial foot amputations, as it says here, leave your patients with an imbalance of muscle in the foot. The gastrocnemius and soleus, they're always going to be there and attached to the calcaneus. And so when you get rid of the flexor digitorum longus and extensor digitorum longus, extensor hallucis longus, flexor hallucis longus, and you cut those, they insert on the distal toes here. You're going to have a lot of problems when it comes to balancing the foot up in the sagittal plane. So there are some things that you really need to consider and you should do on a regular basis with all partial feet patients. One is this red area down here. You really need to support what's left of the amputation site. This needs to be supported very highly there. It almost looks like the foot is in dorsiflexion. because if you cut off this part of the foot right here, it looks like this is going up a little bit. There's an upward arc this way, and you never really see this part here. But because of the presence of the gastrocnemius and soleus, this is going to be pulling up on that, which is going to be driving the cut into the bone down into the floor, down into the base of the shoe, and you really need to support that in order to make a viable alternative to that amputation. The other thing that you need to do is realize that the weight line will shift. The weight line is somewhere between in the cuneiform area here in a normal foot, and then when they amputate that, it moves in this direction quite convincingly back. If you want to find out how it feels to be a partial foot amputee, just stand up right now and try balancing on your heels, and you'll see that it's really a difficult thing to do. The reason it's difficult is because you have a decreased weight bearing surface, and you're not using your digitorum longus in any form, flexor or extensor, to kind of affect your balance. You know what I mean? So it's really, if you want to be empathetic and find out what they're actually going through, is just try walking around on your heels for a few minutes, and you'll get the idea what it feels like. You really have a hard time balancing well by walking on your heels, and it takes a lot of energy to do so. So that's the reason for an anterior shell. You want the partial foot amputee to lean into the anterior shell and reestablish that weight line where it used to be, and you can do that by making them a fairly substantial anterior shell that will bear the weight of that. But keep that in mind when you come across partial foot patients. Giving them a toe filler or a carbon plate with a toe filler attached, I think is a disservice, and really doesn't help them long term. They will probably go into an equinus contracture because you've got this tremendous pull of the gastrocnemius and soleus, and let me go back to that. And that's just, so they may wind up with equinus contractures over time. They may wind up with equinovarus over time, depending upon what muscles have been cut. But typically, tibialis anterior is left intact, and that pulls medially. So equinovarus is something that is very typical of partial foot patients. But keep that in mind, and we have these very lightweight alternatives that work well for this population of patients. Here's a little guy here. He's 11 years old. He's had some skin grafts and burns, and he's got some skin problems. You can tell here that he's been walking on his knees quite a bit. He's got some fairly substantial calluses there. These are the TMA partial foot designs that we've made for him, and he does pretty well. Doesn't seem to be too bothered by any sensitivity on the bottom of his feet. So this is kind of a gray area. It's between orthotics and prosthetics. This is mainly an AFO style solution to partial foot patients, and the other design that we have is more of a posterior opening Symes solution to that as well. Just depends on the length that the patient has in front of the tibia is basically it. But other than the fact that he has little internal rotation issues and he needs to be stretched a little bit for that, this guy does pretty well with this design. If you're confused about what design to use when, we have all of these clinical guides available on our website. So keep that in mind. They're on the home page of our website. I want to talk a little bit about digital workflow at the end here, and scanning has become more and more widely accepted, I think, in the O&P field, and We've bought several scanners. We spent an awful lot of money on scanning. We use scanning for a different purpose. One is for digital archiving, and basically is what our purpose is, because we don't see patients, we're a manufacturer. But blue light scanning or white light scanning used to involve these little boxes that used to carry all these cords and stuff in, and you would have to have a laptop that would be hooked up to this. And this became a little bit laborsome in terms of it's still portable, but it's a little bit of hassle. These were not cheap. These were in the $25,000 to $30,000 range, so there was quite a bit of investment involved in that. The iPad scanner has been out for a few years now, and we have an app. The TechMed 3D app is something that we have available. If you want to download the TechMed 3D app from the App Store, it only works on Apple devices, which is basically an iPad, not even on the phone, just on the iPad. And that has been, this is much cheaper than the white light scanner. I think you can probably buy an iPad for $400, and the scanner is about $450, $500. So for under $1,000, you can get into the scanning game by using an iPad and the TechMed 3D app. Comb has come out with an app that you can use on your iPhone. I think it has to be iPhone 10 or better. It uses the face recognition technology on the front camera of an iPhone. And that's probably the most portable. You could fit that thing in your pocket, and it uploads the file to a cloud-based server. And then the end is that it produces a CTL file that we can use to mill out your AFO shape. This is our TechMed 3D app. You'll have this logo in the top after you set it up properly. We have a PDF that you can use to figure out how to set it up, but a lot of people, I should say more and more people, are sending us scans now than ever. And Russ will talk to his method of how to send scans in the way he does it. He actually takes a cast because he wants to control the ankle, and then he scans the cast and sends that to us. We do have a way of we have developed a way of taking a weight-bearing scanning, and one of it has to do with elevating the foot off of the floor with a piece of foam right here. We do that for a couple of reasons. We want to see the perimeter of the foot, okay, and we also want to simulate the heel height of the shoe. And then we want to check the alignment. So this should be a perpendicular to the floor alignment. Oh, sorry about that. Perpendicular to the floor in the alignment there. And once that is all established, then we can go ahead and take a scan with the iPad. These are some of our summer interns that we have, and they come throughout the summer to help do things. I don't recommend bending over like this girl Janet is doing. She's a volleyball player, and she's 6'4", so she has to bend over quite a bit. But this is the kind of scan you're going to get. You get this white scan, and then the foam that's underneath the foot is clearly visible. And all of this is important in terms of how we want you to take the scan in order to get a good result. We need to have some type of weight bearing in either the cast or the scan, because that tells us what happens to the ankle joint when it's loaded. And that's a critical fitting component. If you want something to fit well and function well, we need to know what happens when the ankle is loaded. So keep that in mind, whether you use a cast or whether you use a scanning device of some kind. And this is the result you're going to get when you get done. It'll incorporate some of the floor into the scan. That's fine. This is very easily to trim away in software, and we can cut the top of this. So we trim it here, and we trim all this stuff away here, and we know what the heel height is here. So all of that is fine, but this is a pretty easy way of getting a scan to us or getting a shape to us. The benefit of the iPad app, obviously, is that you can send notes and you can send photos along with your scan if you've got a very complicated patient that needs a lot of notes. And it also has an integrated order form into the app as well. You just have to follow the prompts to fill out the order form and send us notes or pictures of your patient as well. And then once you get that, we put it in into our milling machine. We can mill out that shape from your scan. One last thing has to do with L codes. L2755 is the one that talks about pre-preg composites right here. And the one thing I wanted to point out is that you can use this L code twice in all of our AFOs, whether they have a joint or not. It's because it's per segment. Okay, so keep in mind that you can use L2755 on every single AFO design that we have, even if it doesn't have a joint, because the foot section is considered one segment, the leg section is considered a different segment. If you have a KFO, you're going to have a thigh, a leg, and a foot. So there'll be three. You can use that 3 times with a KFO. Keep that in mind, because oftentimes that will determine how much you're able to charge for a composite AFO. Well, that was a little bit of a rushed idea, but hang in there, and I will send it back to Rich. Are you there, Rich?
Barry, you're good?
I'm all set. Yep, thank you.
Awesome. All right, great job. Everybody pop over to the other room. We're going to stop this session and start Ross's session with all of the case studies. So good job. So you can pop out too. So Barry, I'm going to stop streaming and it'll tell you the next room.
Okay.